Good evening, friends, and welcome to Sleepy Time Tales, a podcast aimed at helping you to get a good night's sleep. Do you find your mind plagued with the stresses of modern life, especially when the lights are out and you're trying to get a restful night? Does your spinning mind keep you awake? Follow my voice down the path towards a good night's rest. Listen to me tell a story that will keep your mind from wandering to your daytime problems, the ones you can't solve right now, and will be easier to solve while rested. Listen to my voice and allow yourself to drift, following the twists and turns of the story, but slowly letting go and drifting into sleep. So what exactly is Sleepy Time Tales? What is it for? What is this strange thing, this strange idea, this podcast that you're supposed to fall asleep to? But lack of sleep is a health crisis in the 21st century, and this is a podcast intended to help those that it can to get a restful night. Do you find yourself lying awake at night, mind spinning and emotions in turmoil with anxieties of 21st century life? Do you wake up in the middle of the night and find yourself not quite able to doze back off for 3 a.m.? I'm here to help. My name is Dave, and I'm your narrator, here to help you into a restful night. Sleepy Time Tales is intended mainly to be used as a distraction to what keeps you awake at night. But sometimes you might need to use it as background noise or simply company. That's why I make these episodes quite long, so that I'm here for you without any pressure of the end coming. As far as I know, there are a couple of different ways to engage with the show. The main idea behind it is that it gives you something to focus on, a story or an event that lets you keep your mind on a specific point, to stop it from spinning out into stress and anxieties, to help you to focus just enough not to resist the embrace of a night's sleep. A second way is maybe you just need some kind of background noise. Sometimes people like white noise, or the sound of a fan, or the sound of the ocean, or the wind in the trees, or maybe some boring dude just droning on in the background. What matters though is that you don't try force the sleep. Just keep a light mental grip on the thread of the story and allow the need for sleep to come for you. Now obviously if all goes well, I'm hoping you're going to be asleep before we get to the end of the episode. But it's important that you don't feel pressurized. If this is your first night with us, this probably actually won't work for you. It could take you a few nights to get used to listening to my voice, to my accent, to the strangeness of the idea of listening to someone who's going to talk to you while you're asleep. Or maybe your problem isn't going to sleep. Maybe you wake up in the middle of the night. What I recommend you do, because this is what actually happens with me, is download a whole bunch of episodes, put them into your podcast player of choice. When you go to bed, let them go. And then when you wake up at 3 a.m., you find yourself in the dark and lying awake. Just carry on listening. Go back to sleep again. You can even do the same thing if you find yourself waking up before your alarm, 60 minutes or as little as 30 minutes before that. Just carry on listening, fall asleep again. And you may wonder what the point is. How useful is another 60 minutes or 30 minutes of sleep? But I don't know what it is, but there's something about allowing yourself complete relaxation right before the alarm that's satisfying in a whole new level. So lie back and try to relax. If you're new to the show and prone to late nights lying staring at the ceiling, this will probably seem strange to you. So give it a chance. Because I'm here to work with you, to create a safe space, a cocoon in which you can curl up and allow nature to take its course. So if you're still with me, thank you for staying. If you're already asleep, we'll chat again soon. And of course, you aren't hearing me, except maybe in a dream. Before we get on with the show, I'd like to ask for a couple of minutes of your time. We have our special offer running with sleep phones at the moment. That ends at the end of September, so please don't miss out. That is 10% off any purchase of $99.95 or more using the link in the show notes and the promo code SleepyTime when you check out. That $99.95 is the price of a wireless pair of sleep phones, or even like 3 wired pairs and a couple of accessories, so you can either get yourself a wireless one or buy a whole set for the family for that value. And this will help support Sleepy Time Tales and help me keep the show going, as well as helping you to sleep comfortably at night while you listen to this show or anything else that you use at night. Other ways to help support Sleepy Time Tales, of course, are the more direct ones, like the Patreon, which is the monthly support. There's the tip jar on the website. The links to those are up on the show notes. You can go check those out anytime. Thanks to Alima for signing up on the Patreon this week. It's much appreciated. Thank you, Alima. Thank you for joining the family and helping to help me to keep this going. And it's very much appreciated. And of course, another way to help out Sleepy Time Tales is simply to spread the word. You can help me help people to get a good night's sleep, but just telling them about it. If you know someone who's struggling and needs a hand, just mention it. And if you do it on social media, make sure to tag me in. That's at Sleepy Time Tales on Instagram or Twitter, so that I can see and I can thank you. And last but not least, as always, I've got to shout out the music, which is Sweet Night and Friends by Kumiko. Their music is available on their website at loyaltyfreakmusic.com. Thank you very much. Let's get back to the show. We return this week to Astronomy, The Science of the Heavenly Bodies by David P. Todd. Chapter 15, After Newton. We have said that practically all the motions in the solar system have been accounted for by the Newtonian law of gravitation. It will be of interest to inquire into the instances that led to qualification of this absolute statement. One relates to the planet Mercury, whose orbit or path around the Sun is the most elliptical of all the planetary orbits. This will be explained a little later. The Moon has given the mathematical astronomers more trouble than any other of the celestial bodies. For one reason, because it is nearest to us, and very minute deviations in its motion are therefore detectable. Halley it was who ascertained 2 centuries ago that the Moon's motion around the Earth was not uniform, but subject to a slight acceleration which greatly puzzled Lagrange and Laplace, because they had proved exactly this sort of thing to be impossible, unless indeed the body in question should be acted on by some other force than gravitation. But Laplace finally traced the cause to the secular or very slow reduction in the eccentricity of the Earth's own orbit. The Sun's action on the Moon was indeed progressively changing from century to century, in such a manner as to accelerate the Moon's own motion in its orbit around the Earth. Adams, the eminent English astronomer, revised the calculations of Laplace, and found the effect in question only half as great as Laplace had done. And for years, a great mathematical battle was on between the greatest of astronomical experts in this field of research. Adams, in conjunction with Delaunay, the greatest of the French mathematicians a half-century ago, won the battle insofar as the mathematical calculations were concerned. But the Moon continues to the present day her slight and perplexing deviation, as if perhaps our standard timekeeper, the Earth, by its rotation around its axis, were itself subject to variation. Although many investigations have been made of the uniformity of the Earth's rotation, no such irregularity has been detected, and this unexplained variation of the Moon's motion is one of the unsolved problems of the gravitational astronomer of today. But we're passing over the most impressive of all the earlier researches of Lagrange and Laplace, which concerned the exceedingly slow changes, technically called the secular variations, of the elements of the planetary orbits. These elements are geometrical relations which indicate the form of the orbit, the size of the orbit, and its position in space. And it was found that none of these relations or quantities are constant in amount or direction, but that all, with but one exception, are subject to very slow or secular change or oscillation. This question assumed an alarming significance at an early day, particularly as it affected the eccentricity of the Earth's orbit around the Sun. Should it be possible for this element to go on increasing for indefinite ages? Clearly the Earth's orbit would become more and more elliptical, and the Sun would come nearer and nearer at perihelion, and the Earth would drift further and further from the Sun at aphelion, until the extremes of temperature would bring all forms of life on the Earth to an end. The refined and powerful analysis of Lagrange, however, soon allayed the fears of humanity by accounting for these slow progressive changes as merely part of the regular system of mere oscillations, in entire accord with the operation of the law of gravitation, and extending throughout the entire planetary system. Indeed, the periods of these oscillations were so vast that none of them were shorter than 50,000 years, while they ranged up to 2 million years in length. Great clocks of eternity which beat ages as ours beat seconds. About a century ago, an eminent lecturer on astronomy told his audience that the problem of weighing the planets might readily be one that would seem wholly impossible to solve. To measure their sizes and distances might well be done, but actually to ascertain how many tons they weigh, never. Yet if a planet is fortunate enough to have one satellite or more, the astronomer's method of weighing the planets is exceedingly simple. And all the major planets have satellites, except the two interior ones, Mercury and Venus. As the satellite travels round its primary, just as the Moon does round the Earth, two elements of its orbit need to be ascertained, and only two. First, the mean distance of the satellite from its primary, and second, the time of revolution around it. Now it is simply a case of applying Kepler's third law. First take the cube of the satellite's distance and divide it by the square of the time of revolution. Similarly, take the cube of the planet's distance from the Sun and divide by the square of the planet's time of revolution around him. The proportion then of the first quotient to the second shows the relation of the mass, and that is the weight, of the planet to that of the Sun. In the case of Jupiter, we should find it to be 1050, and that of Saturn 3500, and so on. The range of planetary masses, in fact, is very curious, and is doubtless of much significance in the cosmogony, with which we deal later. If we consider the Sun and its 8 planets, the mass or weight of each of the 9 bodies far exceeds the combined mass of all the others, which are lighter than itself. To illustrate, suppose we take as our unit of weight the 1/1000th part of the Sun's weight. Then the planets in the order of their masses will be Mercury, Mars, Venus, Earth, Uranus, Neptune, Saturn, and Jupiter. According to their relative masses then, Mercury being a 5 millionth part the weight of the Sun, will be represented by 200. Similarly, Venus, a 425,000th part by 2,350, and so on. Curious and interesting it is that Saturn is nearly 3 times as heavy as the 6 lighter planets taken together. Jupiter between 2 and 3 times heavier than all the other planets combined, while the Sun's mass is 750 times that of all the great planets of his system rolled into one. All the foregoing masses, except those of Mercury and Venus, are pretty accurately known, because they were found by the satellite method just indicated. Mercury's mass is found by its disturbing effects on Encke's comet whenever it approaches very near. The mass of Venus is ascertained by the perturbations in the orbital motion of the Earth. In such cases, the Newtonian law of gravitation forms the basis of the intricate and tedious calculations necessary to find out the mass by this indirect method. Its inferiority to the satellite method was strikingly shown at the observatory in Washington, soon after the satellites of Mars were discovered in 1877. The inaccurate mass of that planet, as previously known by months of computation, based upon years and years of observation, was immediately discarded in favor of the new mass derived from the distance and period of the outer satellite by only a few minutes' calculation. In weighing the planets, astronomers always use the Sun as the unit. What then is the Sun's own weight? Obviously, the law of gravitation answers this question. If we compare the Sun's attraction with the Earth's at equal distances, first we conceive of the Sun's mass as if all compressed into a globe the size of the Earth, and calculate how far a body at the surface of this globe would fall in 1 second. The relation of this number to 16.1 feet, the distance a body falls in 1 second on the actual Earth, is about 330,000, which is therefore the number of times the Sun's weight exceeds that of the Earth. A word may be added regarding the force of gravitation and what it really is. As a matter of fact, Newton did not concern himself in the least with this inquiry, and says so very definitely. What he did was to discover the law according to which gravitation acts everywhere throughout the solar system. And although many physicists have endeavored to find out what gravitation really is, its cause is not yet known. In some manner as yet mysterious, it acts instantaneously over distances great and small alike, and no substance has been found which, if we interpose between two bodies, has in any degree the effect of interrupting the gravitational tendency toward each other. While the Newtonian law of gravitation has been accepted as true because it explained and accounted for all the motions of the heavenly bodies, even including such motions of the stars as have been subjected to observation, astronomers have for a long time recognized that quite possibly the law might not be absolutely exact in a mathematical sense, and that deviations from it would surely make their appearance in time. A crude instance of this was suggested about a century ago, when the planet Uranus was found to be deviating from the path marked out for it by Bouvard's tables, based on the Newtonian law. And the theory was advocated by many astronomers that this law, while operant at the medium distances from the Sun where the planets within Jupiter and Saturn travel, could not be expected to hold absolutely true at the vast distance of Uranus and beyond. The discovery of Neptune in 1846, however, put an end to all such speculation, and has universally been regarded as an extraordinary verification of the law, as indeed it is. When, however, Leverrier investigated the orbit of Mercury, he found an excess of motion in the perihelion point of the planet's orbit, which neither he nor subsequent investigators have been able to account for by Newtonian gravitation, pure and simple. If Newton's theory is absolutely true, the excess motion of Mercury's perihelion remains a mystery. Only one theory has been advanced to account for this discrepancy, and that is the Einstein theory of gravitation. This ingenious speculation was first propounded in comprehensive form nearly 15 years ago, and its author has developed from it mathematical formulae which appear to yield results even more precise than those based on the Newtonian theory. In expressing the difference between the laws of gravitation in his own conception, Einstein says, "Imagine the Earth removed, and in its place suspended a box as big as a moon, or a whole house, and inside a man naturally floating in the center, there being no force whatever pulling him. Imagine further this box being, by rope or other contrivance, suddenly jerked to one side, which is scientifically termed deformed motion, as opposed to uniform motion. The person would then naturally reach bottom on the opposite side. The result would consequently be the same as if he obeyed Newton's law of gravitation, while in fact there is no gravitation exerted whatever, which proves that deformed motion will in every case produce the same effects as gravitation. The term relativity refers to time and space. According to Galileo and Newton, time and space were absolute entities, and the moving systems of the universe were dependent on this absolute time and space. On this conception was built the science of mathematics. The resulting formulas sufficed for all motions of a slow nature. It was found, however, that they would not conform to the rapid motions apparent in electrodynamics. Briefly, the theory of special relativity discards absolute time and space, and makes them in every instance relative to moving systems. By this theory, all phenomena in electrodynamics, as well as mechanics, hitherto irreducible by the old formulae, were satisfactorily explained. Natural phenomena then involving gravitation and inertia, as in the planetary motions, and electromagnetic phenomena, including the motion of light, are to be regarded as interrelated and not independent of one another. And the Einstein theory would appear to have received a striking verification in both these fields. On this theory, the Newton dynamics fails when the velocities concerned are a near approach to that of light. The Newtonian theory then is not to be considered as wrong, but in the light of a first approximation. Applying the new theory to the case of the motion of Mercury's perihelion, it is found to account for this excess quite exactly. On the electromagnetic side, including also the motion of light, a total eclipse of the sun affords an especially favorable occasion for applying the critical test. Whether a huge mass like the sun would or would not deflect it toward itself, the rays of light from stars passing close to the edge of its disk or limb. A total eclipse of exceptional duration occurred on May 29, 1919, and the two eclipse parties sent out by the Royal Society of London and the Royal Astronomical Society were equipped especially with apparatus for making this test. Their stations were one on the east coast of Brazil and the other on the west coast of Africa. Accurate calculation beforehand showed just where the sun would be among the stars at the time of the eclipse, so that star plates of this region were taken in England before the expeditions went out. Then during the total eclipse, the same regions were photographed with the eclipsed sun and the corona projected against them. To make doubly sure, the stars were a third time photographed some weeks after the eclipse, when the sun had moved away from that particular region. Measuring up the three sets of plates, it was found that an appreciable deflection of the light of the stars nearest alongside the sun actually exists, and the amount of it is such as to afford a fair, though not absolutely exact, verification of the theory. The observed deflection may of course be due to other causes, but the English astronomers generally regard the near verification as a triumph for the Einstein theory. Astronomers are already beginning preparations for a repetition of the eclipse program, with all possible refinement of observation, when the next total eclipse of the sun occurs, September 20th, 2022. Visible in Australia and the islands of the Indian Ocean. A third test of the theory is perhaps more critical than either of the others, and this necessitates a displacement of spectral lines in a gravitational field toward the red end of the spectrum. But the experts who have so far made measures for detecting such displacement disagree as to its actual existence. The work of St. John at Mount Wilson is unfavorable to the theory, as is that of Evershed of Kodaikanal, who has made repeated tests on the spectrum of Venus, as well as in the cyanogen bands of the Sun. The enthusiastic advocates of the Einstein theory hold that, as Newton proved the three laws of Kepler to be special cases of his general law, so the universal relativity theory will enable eventually the Newtonian law to be deduced from the Einstein theory. This is the way we go on in science, as in everything else, wrote Sir George Airy, Astronomer Royal. We have to make out that something is true. Then we find out under certain circumstances that it is not quite true. And then we have to consider and find out how the departure can be explained. Meanwhile, the prudent person keeps the open mind. Chapter 16. Halley and his Comet. Halley is one of the most picturesque characters in all astronomical history. Next to Newton himself, he was most intimately concerned in giving the Newtonian law to the world. Edmond Halley was born 1656 in stirring times. Charles I had just been executed, and it was the era of Cromwell's Lord Protectorate, and the wars with Spain and Holland. Then followed, in 1660, the promising but profligate Charles II, who nevertheless founded at Greenwich the greatest of all observatories when Halley was 19. The frightful ravages of the Black Plague, the tyrannies of James II, and the Revolution of 1688. All in the early manhood of Halley, whose scientific life and works marched with much of the vigor of the contending personalities of state. The telescope had been invented a half-century earlier, and Galileo's discoveries of Jupiter's moons and the phases of Venus had firmly established the sun-centered theory of Copernicus. The sun's distance, though, was known but crudely, and why the stars seemed to have no yearly orbits of their own corresponding to that of the Earth was a puzzle. Newton was well advanced towards his supreme discovery of the law of universal gravitation, and the authority of Kepler taught that comets travel helter-skelter through space, in straight lines past the Earth, a perpetual menace to humanity. Ugly monsters that comets always were to the ancient world. The medieval church perpetuated this misconception so vigorously that even now these harmless, gauzy visitors from interstellar space possess a certain wizard hold upon our imagination. This entertaining phase of the subject is excellently treated in President Andrew G. White's History of the Doctrine of Comets, in the papers of the American Historical Association. Halley's brilliant comet at its earlier apparitions had been no exception. Halley's father was a wealthy London soap maker who took great pride in the growing intellectuality of his son. Graduating at Queen's College, Oxford, the latter began his astronomical labours at 20 by publishing a work on planetary orbits, and the next year he voyaged to St. Helena to catalogue the stars of the southern firmament, to measure the force of terrestrial gravity, and observe a transit of Mercury over the disk of the Sun. While clouds seriously interfered with his observations on that lonely isle, what he saw of the transit led to his invention of Halley's method, which, as applied to the transit of Venus, though not so long after his death, helped greatly in the accurate determination of the Sun's distance from the Earth. Halley's researches on the proper motions of the stars of both hemispheres soon made him famous, and it was said of him, "If any star gets displaced on the globe, Halley will presently find it out." His return to London and election to the Royal Society, of which he was many years secretary, added much to his fame, and he was commissioned by the Society to visit Danzig and arbitrate an astronomical controversy between Hooke and Hevelius, both his seniors by generation. On the continent he associated with other great astronomers, especially Cassini, who had already found 3 Saturnian moons, and it was then he observed the great comet of 1680, which led up to the most famous event of Halley's life. The seer-like Seneca may almost be said to have predicted the advent of Halley when he wrote, "Someday there will arise a man who will demonstrate in what region of the heavens comets pursue their way, why they travel apart from the planets, and what their sizes and constitution are. Then posterity will be amazed that simple things of this sort were not explained before." To Newton it appeared probable that cometary voyages through space might have orbits of their own, and he proved that the comet of 1680 never swerved from such a path. As it could nowhere approach within the moon's orbit, clearly threats of its wrecking the Earth and punishing its inhabitants ought to frighten no more. Halley then became intensely interested in comets, and gathered whatever data concerning the paths of all these bodies he could find. His first great discovery was that the comets seen in 1531 by Appian and in 1607 by Kepler traveled around the Sun in identical paths with one he had himself observed in 1682. A still earlier appearance of Halley's comet, 1456, seems to have given due to a popular and long reiterated myth of a papal bull excommunicating the devil, the Turk, and the comet. No longer room for doubt. So certain was Halley that all 3 were one and the same comet, completing the round of its orbit in about 76 years, that he fearlessly predicted that it would be seen again in 1758 or 1759. and with equal confidence he might have foretold its return in 1835 and 1910. For all three predictions have come true to the letter. Halley's span of existence did not permit his living to see even the first of these now historic verifications. But we in our day may emphatically term the epoch of the third verified return Annus Hallianus. Says Turner, Halley's successor in the civilian chair at Oxford today, there can be no more complete or sensational proof of a scientific law than to predict events by means of it. Halley was deservedly the first to perform this great service for Newton's law of gravitation, and he would have rejoiced to think how conspicuous a part England was to play in the subsequent prediction of the existence of Neptune. Halley rose rapidly among the chief astronomical figures of his day, but he had little veneration for mere authority, and the significant veering of his religious views towards heterodoxy was for years an obstacle to his advance. Still, Halley, the astronomer, was great enough to question any contemporary dicta that seemed to rest on authority alone. Everyone called the stars fixed stars, but Halley, doubting this, made the first discovery of a star's individual motion, proper motion, as astronomers say. Today, 200 years after, every star is considered to be in motion, and astronomers are ascertaining their real motions in the celestial spaces to a nicety undreamed of by even the exacting Halley. The moon, of priceless service to early navigators, was regarded by all astronomers as endowed with an average rate of motion around the Earth that did not vary from age to age. But Halley questioned this too, and on discovering the ancient value from Chaldean eclipses, he made another discovery: the secular acceleration of the moon's mean motion, as it is technically termed. This was a colossal discovery in celestial dynamics, and the reason underlying it lay hidden in Newton's law for yet another century, till the keener mathematics of Laplace detected its true origin. With Newton, Halley laid down the firm foundations of celestial mechanics, and they pushed the science as far as the mathematics of their day would permit. Halley, however, was not content with elucidating the motion of bodies nearest the Earth, and pressed to the utmost confines of the solar system known to him. Here too he made a signal discovery of that mutual disturbance of the planets in their motion round the Sun, called the great inequality of Jupiter and Saturn. Halley's versatile genius attacked all the great problems of the day. His observation of the Sun's total eclipse in 1715 is the earliest reliable account of such a phenomenon by a trained astronomer. He described the corona minutely, and was the first to see that other interesting phenomenon, which only an alert observer can detect, which a great astronomer of a later day compared to the ignition of a fine train of gunpowder, and which has ever since borne the name of Bailey's beads. Besides being a great astronomer, Halley was a man of affairs as well, which Newton, although the greater mathematician, was not. Without Halley, Newton's superb discovery might easily have been lost to the age and nation, for the latter was bent merely on making discoveries, and on speculative contemplation of them, with never a thought of publishing to the world. Halley, more practical and businesslike, insisted on careful writing out and publication. Newton was then only 42, and Halley fully 14 years his junior. But the philosophers of that day were keenly alive to the mystery of Kepler's laws, and Halley was fully conscious of the grandeur and far-reaching significance of Newton's great generalization, which embodied all three of Kepler's laws in one. Newton at last yielded, though reluctantly, and the Principia was given to the world, though wholly at Halley's private charges. But Halley was far from being completely engrossed with the absorbing problems of the sky. Things terrestrial held for years his undivided attention. Imagine present-day Lords Commissioners of the Admiralty entrusting a ship of the British Navy to civilian command. Yet such was their confidence in Halley that he was commissioned as captain of HM's Pink Paramour in 1698, with instructions to proceed then to the southern seas for geographical discoveries, and for improving knowledge of the longitude problem, and of the variations of the compass. Trade winds and monsoons, charts of magnetic variation, tides and surveys of the Channel coast, and experiments with diving bells were practical activities that occupied his attention. Halley in 1720 became Astronomer Royal. He was the second incumbent of this great office, but the first to supply the Royal Observatory with instruments of its own, some of which adorn its walls even today. His long series of lunar observations and his magnetic researches were of immense practical value in navigation. Halley lived to a ripe old age and left the world vastly better than he found it. His rise from humblest obscurity was most remarkable, and he lived to gratify all the ambitions of his early manhood. Of attractive appearance, pleasing manners, and ready wit, says one of his biographers. Loyal, generous, and free from self-seeking, he was one of the most personally engaging men who ever held the office of the Astronomer Royal. He died in office at Greenwich in 1742. Halley was buried, says Chambers, in the churchyard of St. Margaret's Lee, not far from Greenwich, and it has lately been announced that the Admiralty have decided to repair his tomb at the public expense, no descendants of his being known. There is no suitable monument in England to the memory of one of her greatest scientific men. In any event, the collection and republication of his epoch-making papers would be welcomed by astronomers of every nation. And with the passing of Edmond Halley, I'm going to call it a night. This was a rather interesting read tonight. I even did some research on some of the funny topics that popped up as I went along. So if you'd like to pick up where we've left off, as always, you can find it on Project Gutenberg at the link in the show notes. Thanks again for joining me on this episode of Sleepytime Tales, the podcast designed around a bedtime story to help you to get a restful night. New episodes will be released every Sunday night to give you something fresh to help you rest in a new week. But make sure to follow or subscribe in whatever service you use so that you get your new episodes whenever they come out. A reminder that the music for tonight is Sweet Night and Friends by Kumiko. Check out more of their work on their website, which you'll find linked in the show notes. Good night, and sweet dreams.